University, Calcutta in 1996 and received the master degree with honors in electrical engineering with specialization in high voltage engineering in 1999. He was rank holder in both. He received the PhD degree from Durgapur University in 2003. Dr. De has more than 20 years of undergraduate and postgraduate teaching and research experience in State University and centrally funded technical institute. He also has 5 years of experience of working in the industries. He has authored in 3 textbooks and 12 book chapters published by reputed international publishing houses. Dr. De has active research interest in power system operation, monitoring and control, power system transient, power system stability and security, high voltage engineering, insulation coordination, condition monitoring and fault diagnosis, pattern recognition and machine learning. Dr. De has guided 9 PhD research scholars and presently guiding few more PhD scholars. Dr. De has more than 100 research publications in international and national journals and conferences, including transaction of the IEEE, proceeding of the IIT and elsewhere. He has been awarded the Best Paper Award 3 times. He has delivered keynote address and invited lectures in more than 50 national and international conferences, workshops and training programs organized by different NITs, central and state universities and academic institutes. He has served as track chair and session chair in more than 10 reputed international and national conferences. He has successfully executed 3 numbers of government-sponsored research projects and has also rendered expert services in a number of consultancy projects. Dr. De has served as expert member of the doctoral committee of different NITs and universities and expert member in the board of studies of different academic institutes. He has presently working as associate professor in the Department of Electrical Engineering, Indian Institute of Engineering Science and Technology, that is IIEST Shibpur. Now, sir, stage is yours.
Engineering College, Professor C.K. Chandra, ACT Professor, IIEST Shibpur, Head of the Department, Electrical Engineering, BCREC College, and the coordinator of this Faculty Development Program, Professor Shubit Banerjee, all the participants from different institutes of the state and outside. So, very good morning to all of you. So, it's a great privilege for me, and I thank the organizers for giving me this opportunity to interact with you on this prestigious ATAL-FDP platform. And I would also like to congratulate the organizing team for winning this prestigious FDP because as I come to know that this time it was only 395 proposals that were accepted by the government, and that is generally the case that normally these ATAL-FDP, they are generally being approved for the government institutes. So being a non-government institute winning an ATAL-FDP proposal, that's quite a commendable job, and I again congratulate the team for that. Okay, so today my topic of presentation broadly is the application of computational intelligence in the domain of electrical power system. So I belong to the domain of electrical power system. So although I believe that the audience present over here should be coming from the diverse background, right? So I would try to keep my presentation as general as possible so that it becomes comprehensive to the participants from other backgrounds as well. So just to have a broader background, that the electrical engineering domain and specifically the power system has undergone tremendous change, right, over the last few decades. So if we just analyze that what are the major thrust areas where the changes are occurring, then probably the most important one is the large-scale integration of the renewable energy sources. Right? So we know that like other countries of the world, our country also has a very ambitious plan of integrating renewable sources into the existing system. And we are now aiming to add hundreds of gigawatts of renewable sources coming from like say solar, wind and other resources. So that definitely it has brought new challenges for the power system engineers, because earlier our traditional electrical grid and electrical power supply system used to run in a somewhat traditional manner, whereas this integration of very large scale renewable energy has brought new challenges. Right? And therefore, the whole power system has to be also modernized, and there has to be revolutionary changes which has to be incorporated. And machine learning is one of them. Coming to the other major areas where the changes are coming, we have seen that we are moving to the incorporation of IT and IoT infrastructure, right, in the day-to-day operation of the electrical systems. So the concept of smart grid, smart technologies incorporated in the electrical power and energy sector, that has again been quite a new area. So we have seen that the grids are becoming smarter, right? The smart controls, smart metering, and even in the distribution and consumer level, we are seeing that nowadays there are a lot of applications of IT and IoT infrastructure. Again, we also realize that the electrical power system, particularly in a country like India, which has a very diverse geographical spread, the electrical grid actually spans over large geographical area. It's a huge electrical grid. So we also realize that as the grid is increasing in size and it is becoming more and more intricate, so the control, monitoring of the grid and the corrective measures in the event of adversity, that is also becoming more and more challenging. Right? So we have brought into different control actions into the grid, the wide area monitoring with the advent of the phasor measurement unit or the synchrophasor, right? That has also brought new area in the power system. So earlier we traditionally used to be more dependent on devices like SCADA and all that, but this which came as a pilot project a few decades back, this phasor measurement unit or the synchrophasors, that has given new direction to the power system monitoring and control. We also realize that as the grid is increasing in size, so at some point of time it becomes really difficult to manage such a large grid. So we also tried to decentralize the generation, distribution and transmission, and gradually we found the advent of mini and micro electrical grids. Right? So that is again another area which is very contemporary, very relevant nowadays. And last but not the least is the integration of artificial intelligence, machine learning, pattern recognition for making the operation of grid more efficient, more reliable. So these are the key areas where the changes are happening, and the changes will be happening over the next decade. Basic definition of this computational intelligence. Although I believe that this artificial intelligence, machine learning, this has become so familiar in our day-to-day life today that it doesn't actually require further introduction or elaboration. So we know that AI, ML, these things are now integrated in every sphere of our life. The mobile device that we use is now being powered by AI, ML. Many intelligent gadgets that we use at our home, these are also being powered by this machine learning and artificial intelligence. Now, coming to the definition, what it says that computational intelligence, this is as per the definition that I received in Wikipedia, that it refers to the ability of a computer to learn a specific task from data or experimental observation. CI, computational intelligence, generally refers to a set of nature-inspired computational methodologies and approaches to address complex real-world problems to which mathematical or traditional modeling can be unsuccessful. In most cases, computational intelligence provides acceptable solution to such problems. So what is the basic inspiration behind the use of computational intelligence or machine intelligence is the fact that what we understand that most of the real world processes that we experience, these are very imprecise and they are often the data that are available or the information that are available are very, I would say, insufficient. So as engineers, we know that when we try to analyze anything, the first thing that we need to develop is a precise mathematical model. For example, if somebody is interested in power system analysis, then probably the task starts with a precise modeling of the power system. Now the problem is that as the system is growing and as the system is becoming more and more intricate, developing a precise mathematical model becomes extremely challenging. And it is not just true for the power system, it is true for any system, any engineering system, any industrial system. So, unless we can develop a precise mathematical model for the system, we know that the analysis that we perform on it will be inaccurate, right? And the results will nowhere be close to the reality. But the problem is that for most of these systems, the real world systems, developing a mathematical model is not an easy task. Right? We can develop models for relatively simpler system, right? And we have tools available for them, but those tools are often insufficient for complex real world system. So then we actually started thinking in a different way, and what it says that this data or experimental observation, in general, this computational intelligence, machine learning, AI, etc., these are called data-driven approaches. So basically, these models are based on the data that we collect. And also, another very significant term is the nature-inspired computational methodologies, because as we progress, we will see that most of these AI or ML techniques, these are somewhere inspired by the biological processes, right? The way the human brain functions, the human nervous system functions, or the nervous system of developed animals function. So we try to somewhat imitate them, right, and replicate the way they function. So moving on to, again coming to some of the realizations that what we see, that if we take the example of visual information processing, this is something that we ongoingly do every day. We see that even a 1-year-old child is far superior and faster in recognizing objects, faces, and different visual features. For example, if we just consider the objects which are present in this room, then we know that all of us, we can easily recognize each and every different object which are present in this room. But the task actually is not at all easy, because if we want to develop a computer program to recognize these objects in a traditional way, then we understand how difficult the thing is. For example, if we want to say, identify a table as a table, right, or a chair as a chair, or a desk as a desk, then the traditional approach that we generally should take is based on the geometry, shape, etc., of the object. But the problem is that the information that we can put into, and based on these information, recognizing the object is really a challenge, because the table can actually have different shapes and the geometry can vary. The length, breadth, height, width, etc. can be different for different tables, chairs, or desks. So the traditional approach of defining objects, recognizing objects simply based on geometry and shape, it's not a very prudent idea, and the computer program written in a traditional manner will fail. But we see that the brain can effortlessly do this. Brain can easily recognize each and every object, and more interestingly, the brain doesn't require explicit instruction for this purpose, right? We can do this without the need for giving any specific instruction. Coming to a more precise example, take some sequence of digits. Right? So we can easily recognize the digits are 504192. Right? So all of us can recognize the digits. So these are basically handwritten characters or handwritten digits. Now, if you just think deeply that how we recognize these digits so effortlessly, so fast, so quick, can you really develop a computer program in the traditional manner which can recognize a handwritten file so fast, so effortlessly, and so quick? The task is not at all easy. Why? Because these are handwritten characters, right? And these handwritten characters look very different from typed characters, right? So you may train your computer to recognize a typed digit like 5 or 0 or 4. But when it comes to a handwritten digit, then so many exceptions, so many variations are possible, because handwriting differs from one person to another. Therefore, the question is, how many different variations you can teach to your computer? Because a computer, when the program is written in a traditional manner, it is nothing but a set of instructions which is given to the computer. So how do you define, say, any digit? For example, take the digit 9. So how do you define 9 as a digit? Then, if you think in a traditional manner, then probably the instruction should look like this, that 9 is a digit which has a loop at the top and a vertical stroke in the bottom right. Now we understand that this instruction is very, very insufficient, right? Because 9 is not something which can be defined so easily, because it can be written in so many different ways. So then we understand that the traditional way of programming, that actually doesn't serve the purpose. So then that comes as the basic inspiration. So then we try to think in a different way, that why not we develop new kind of computing systems which can mimic the functional characteristics of the human brain, or attempt to model the intelligent computing capabilities of the brain. Right? Because we understand that brain has some extraordinary capability, that it can recognize each and every object, each and every digit, each and every character so effortlessly. So something should be there which is different than the computer really does. So let me skip and move forward. So let us take, for example, the artificial neural network, or ANN, which is basically can be perceived as an attempt to model the information processing capabilities of the human nervous system, or the nervous system of developed animals. Now just coming back to the example that I had given, and we found that how difficult it is to write a traditional computer program which can recognize the digit. Now let us take a slightly different approach. And what is that different approach? The different approach is, if you look at this table on the right hand side, you find that here we have actually provided
examples of all these digits, right? And not just one single example, but many examples of each and every individual digit. For example, you can find different variants of every digit. For example, a 0 has been presented here. It has also been presented here and here, or here, right? But each of them is slightly different from the other. And the same thing applies to the other digits also. So what we are really trying to do here, what we are trying to achieve here is that we are providing examples of every handwritten character. And we are providing tens and hundreds and thousands of such examples to the computer with the idea that let the computer learn through example, not through instruction. So again, the idea comes from, take the case of a child. How a child does learn, right? So a newborn child, when he or she just comes to the world, he or she doesn't know anything, right? The whole world is new to him or her. But then, every passing day is a learning experience for the child, right? So the child learns newer things every day. If you talk about the mother tongue, right? The mother tongue need not be taught, right? So the child automatically, by himself or herself, learns the mother tongue. So this natural learning comes because of the people around speaks in that language, right? So suppose somebody is speaking in Bengali around the child, so the child automatically adapts to that language, automatically learns the language. And the learning happens without any supervision or training, right? We don't need to teach the child automatically learns. Why he learns? Because he learns through examples, because others are speaking. So the child is getting many examples that how the words are spoken, how different things are being talked about. So this is how the child learns. So same thing is being replicated here, that instead of giving specific instruction to the computer, let us provide example and let the computer learn through example that, well, 0 is a digit which may either look like this, or it can also look like this, or like that, or like that, or like this. So by this way of providing hundreds of examples, the computer automatically learns how the different digits look like. And once it is properly trained, or it has learned, it can now even interpolate or extrapolate the knowledge that even if I now present a 0, which looks very different from the other examples that already have been presented, but still it can interpolate and extrapolate the knowledge, which we normally call the intelligence. Because we just do not remember the things, we can apply our intelligence to do something even if we are put in an unfamiliar situation. We don't need to have experience of everything or past experience. We can apply our own intelligence to do new things. So I have some basics of biological neural systems, right? I will not talk much on that. I will try to focus mostly on the application part, but just to have some basic ideas that these are the things that we all know, that the biological neural system, we call it a massively parallel system. Just coming to the concept of that, why the biological systems like the human brain or the human nervous system, why it can act so efficiently and it is so much superior compared to the computer system. Now, if you think of the operational speed, we know that the modern day, the computer chips, the CPUs, they actually run very fast, right? They run at a frequency of gigahertz, which is even faster than the way the nervous system works. So the information processing speed, if you think at a chip level, then it is much faster in case of computer. But why then the computer overall, when it comes to solving real world problems, is slower and inefficient as compared to the animal system or the human system? So we are still have not been completely able to analyze the exact way the brain functions, but the neuroscientists, the biologists, they have at least gathered some knowledge, and based on which we can make certain comments, one of which is that one major difference between the way the computer works and this human or biological nervous system works is the difference in the approach. Right? For a computer, everything is basically a data-driven approach. Right? So it's basically the computer perceives everything as data. So whatever information you pass on to your computer, it has to be passed on in the form of some data, right? The bits and bytes. But in case of human being, it is actually not being treated as data, but it is treated as a pattern. So we see that, we say that, and that is basically the observation of the neuroscientists, the biologists, is that whatever we see, right, around us, a replica or some sort of an image of that is being stored in our brain. We call it a mapping process. So through our retina, we take a snapshot or whatever we see. Suppose if I see a person, then a replica or an image of the person is mapped onto certain areas of our brain. And the brain has a very organized way of storing information. Right? There are different cortices in the brain. There are visual cortices, there are auditory cortices. And these cortices store specific information. For example, all these visual information, these are stored onto certain area of the brain. Similarly, whatever we hear, right? So all these, they produce auditory maps, and these maps are again created on certain areas of the brain. So because the things are now mapped onto the brain in the form of images or replica, so in future when you see a person, when you come across a person whom you have seen maybe say several years back, immediately you can match that image of the person with the stored image in your brain, and that happens very fast. Because if this would be done by a computer, then it would probably be a bit by bit analysis, and that would take a long time. That doesn't happen in case of brain. So one major difference is the way that everything is being treated as data by the computer, whereas the human brain treats them as patterns or images. That is one way. The other way is that we know that computers are basically serial processing machines. Right? Because if you think in the chip level, then you know that all these hardware chips that we have, starting from your logic gates, the flip-flops, etc., these are basically sequential machine, or they are basically serial information processing machine. So although we say that the computers are multiprocessing or multitasking in nature, truly speaking, the computer is actually not multitasking or multiprocessing, because ultimately everything is processed serially. But what happens in a computer is that the operating systems and the programs, they are so clever that they basically allocate the resource. There is a clever time allocation and resource allocation between different processes. So a computer takes up a task, partially execute that, and then allocates the resource and time to a different process. Right? So partially executes the next process, and then jumps back to the previous process. So this way the time and resource allocation happens, and that's why it appears that as if the things are being done parallelly. But actually speaking, it's not so. But that's not the case in case of human nervous system or the biological system, where there is actual parallel processing, parallel transmission, parallel analysis of information. So, all this I said in the context that the biological network, the network of biological neurons that we naturally possess in our brain, that is actually a hugely parallel architecture. Because we have billions of neurons in our brain, in our nervous system, these neurons are interconnected, they are massively interconnected through something called synaptic connections. And we know that through the chemical processes, electrochemical processes, through these synaptic connections, the information that we gather from the outside world, these are being transmitted to the brain through this massive parallel architecture of biological neural network. And also at every stage, there is processing of information. So each and every neuron can process information, transmit information, and that's why the overall quickness or such a rapid speed of operation, these are being achieved through this massive parallel processing of information, which doesn't happen in a computer system. So these are some of the basic difference between the way the information, the data is being processed by computer and the data is being processed by the human nervous system. Now, as I said that all these machine learning processes, these try to some way or other replicate or imitate the biological processes. So when we say about an artificial neural network, because the term is an artificial neural network, so it's basically a simulated model of the biological neural network. So now we talk about the simulated neurons and simulated neural network. So what is a simulated neuron? A simulated neuron looks somewhat like this. So a simulated neuron is, if we just think very crudely, then it is nothing but, we call it a summing node, right? Nothing else but a summing node. So what this summing node is doing is that, you can see that it can collect information from various outside sources through various parallel channels by this neuron, the simulated neuron. And you can see that this x0, x1, x2, up to say xn, n can be any number. These are basically the information, or you can say piece of information which are being collected from the external world. And these W's, this W0, W1, W2, etc., these are called the connection weights or weightages. So what is the idea? The idea is that when an information is passed through a certain channel, the information will be multiplied by the corresponding weightage of that particular channel. So if the information is transmitted through this channel, then it will be multiplied by the corresponding weightage, which is W0. When it is being transmitted by, say, this particular channel, it will be multiplied by W1. When it is transmitted by this, it will be multiplied by W2 and so on. So ultimately what you receive in this cell body or this node is basically the aggregate of different weighted values of signals or information, right? So all that you receive is basically W0 x0 plus W1 x1 plus W2 x2 and so on. So now you can consider the cell body or the neuron as a summing log, that it will actually make an aggregate of all these weighted signals that it has received, and now we can call it the weighted sum of all the received signal. Now in addition to this weighted sum, it can also add some sort of a bias term. So here you can see that this B, the term B, is basically called a bias term, which will come more in detail later. So that can also be added to this aggregated sum. Then you find this function f, which is called the output function, also called the activation function. So when the neuron, just think in terms of the biological system, that what a particular neuron does, that every biological neuron is actually being surrounded by thousands and lakhs of other neurons, and these are also being interconnected. So every neuron can receive information from thousands of other neurons which are surrounding it. Then after receiving that particular information, the particular neuron will make an aggregate of all the information that it has collected, and then in turn it will transmit that information to the next neuron. And it will not just transmit the information to one neuron, but it will also transmit to the other neurons which are at its surrounding. So it receives information parallelly from many sources, and it will also transmit that information or a modified version of that information to many other neurons which are in its surrounding. So the same thing is being replicated here, that this activation function will decide that what kind of output that particular neuron will generate. The output will be a function of all the inputs that it has received, and it will also depend on the particular function that we have chosen. So this way, the neuron will receive some input and will produce a corresponding output, which will then be transmitted to many other neurons in its surrounding. Coming to the typical architecture of an artificial neural network, we call it a layered architecture. So it's a very organized architecture. You can see that a basic neural network has many layers, right? So the architecture comprises of several number of layers. In any neural network, there should at least be two layers. One of which is the input layer, and the other one is the output layer. So these two are the mandatory layers which should always be present. In addition, you can also have some intermediate layers which are called hidden layers. So if you consider a neural network as a black box, then only the input layer and the output layer will be visible from outside. The other layers will be deeply embedded inside the box, and they will not be visible from outside, and they will be called hidden layers. So as you can see in this diagram, that every layer comprises of set of neurons, right? Different number of neurons. Now the number of neurons in the input layer will be decided by that how many different information you wish to receive. So suppose if you have an information which has, say, 10 number of components, then you require 10 number of neurons in that input layer, so that each individual neuron can actually accept one particular component of the information. So the number of neurons in the input layer will be pre-decided by your data dimension, right? Similarly, the number of neurons in the output layer will again be decided by that in what form you want your output to be. So if you want your output to be just comprising of one particular element, then you just require one neuron in the output layer. But if you require the output in the form of a vector having many elements or many components, then again the output layer may comprise of several number of neurons. Coming to the hidden layers, the number of neurons in the hidden layers are not pre-decided. We decide during the course of training that how many layers and how many neurons per layer will be sufficient, right? So I have shown just one hidden layer in this diagram, but in reality the neural network can actually comprise of several number of hidden layers. There may be, say, 2, 3, 4, 5 or even more number of hidden layers, and also the number of neurons in the hidden layers are not pre-decided. They are decided during the course of training. Now, because I cannot go much into the details of how the neural network is being trained and the training algorithms, because there are hundreds of different training algorithms, right? So every day new training algorithms are being developed, are being modified. So let us just come to the basics of learning, that how the neural network learns. So as I said, that the learning process in a neural network is very similar to the human learning process. Now, the way the neural network can learn, these are the ways. Right? The neural network can learn by developing new connections. So what is meant by the term connection, if you just come back to this diagram, that as you can see that any particular neuron can actually receive information from all the previous layer neurons. Say for example, take the case of this particular neuron. It can receive information from this neuron through this channel. It can also receive information from this neuron through this particular channel, or through this particular channel, or through this channel. So you can see that every neuron in the subsequent layer is actually connected to all the neurons in the preceding layer, right? So that is true for any layer. For example, if you consider this output layer neuron, again you can see that it can receive information from all the neurons in the preceding layer. Similarly, if you consider how the neuron transmits the information, just take the case of one particular neuron, you will see that transmitted, you can see that this neuron, it can transmit information to this neuron, or to this neuron, or to this neuron, or to this neuron, or to this neuron. So every neuron can transmit information to all the neurons in the subsequent layer, whereas any neuron in a layer can receive information from all the neurons in the preceding layer. So that's how this massive interconnection is generated, and that's how the information is being transmitted and processed through many parallel channels. Now, as I said, that every path has its own corresponding weightages, right? So just to give the broad idea that how the learning process occurs. So I do not have any specific slide because I don't want to go into any specific algorithm, because that will be a very lengthy task, and also it will be somewhat boring because there are so many different learning algorithms. So I will just try to give you the basic idea, and I believe that many of you should be familiar with this topic, so it may be a repetition for you. For those to whom this is a new topic, let us just discuss the basics, and if you develop the interest in the topic, then probably you can go through the books and study material so that you can learn the algorithms in details. So there are two broad categories of learning. One is called the supervised way of learning. The other way is called the unsupervised way of learning. So let us talk about the supervised way of learning first. What is supervised learning? Is that, suppose you want to teach a specific kind of information to the neural network. So what do you do then? So as the term suggests, it's a supervised learning. It means that you have to provide both the input and the output combinations to the neural network, right? So I'll give specific example later on. So you give a set of input conditions and also tell the neural network that if these are the inputs, then this is going to be my output, right? If the input combinations change or the input composition change, then the output will also change, and the changed output will be like this. So this way, you provide many examples of different combinations of the inputs and the corresponding output, right? These are called input-output set or the training data set. So a training data set basically comprises of some known inputs and the corresponding known outputs. That if these are the inputs, this is going to be the output. If the inputs get changed, then this will be the corresponding changed output, right? So this way you gather hundreds of such examples of different combinations of inputs and the corresponding outputs. What you do then? You feed this information to the neural network, right? So you feed this information through these input channels and you get your output from this output neuron. What is the objective? The objective is that let the neural network predict the output corresponding to a set of inputs, right? So we provide a set of input to the neural network and ask the network that you guess what should be the corresponding output. So the neural network will make a guess. How the neural network will make a guess? As I said, that when you provide an input to the first layer of neuron, those information will be transmitted to the next layer, and through this process of transmission, they will be multiplied by the corresponding weightages of the different path. They will again be aggregated at different nodes like this, and then ultimately the whole information will be passed on to the output neuron, and from there we will collect the output. The question is that how do you know that whether the guess which is made by the neural network will be close to the original output, or the, what we say is the target output or the corresponding output. You have provided some set of inputs and you know that corresponding to this input, this is going to be the corresponding output, right, which we call the target output. So we expect the neural network to produce an output or a guess which will be very close to the target output. But initially, an untrained neural network will not be able to produce a guess which will be anywhere close to the target output. We call it the error, right? The difference between the output produced by the neural network and the target output. Now, this error will be utilized to modify the different connection weights of the neural network. Because modification of the connection weights in a systematic manner will result in closer and closer value of the guess. So in the initial guess can be anything, but as the iteration progresses, because training is an iterative process, so during the course of iteration, this connecting weights will be modified, and finally the connecting weights will be optimized. I use the term optimized because the optimal set of weight will give you the best output, which is closest to the target output, right? So that's how the neural network works, that it basically modifies the connection weight, and sometimes it also changes the architecture of the network in the sense that it can add more number of layers if required. It can also delete some layers if required, and it can change the value of the connection weightages. So by this process, it will now gradually try to make closer and closer value of the output, which will be very close to the target. And when the weights are optimized, then the output produced by the neural network should be very close to the target output, right? So that is our objective. Now, the question is, we have given one input and we have modified the weights to produce an output which is close to the target output. Can the same set of weight also work equally well for another set of inputs? Obviously no, right? So when you have tuned your weights to give the best result for one particular set of input, then the same set of weight may not work equally well for the next set of input. So then you remodify your weights. And when we say optimization, the optimization is not just for one set of input, but it works for the whole set of input. So ultimately you achieve a globally optimal set of weight which works not just for one set of input, but for all the input-output combinations that you have. So once you have this optimal set of weight, which works more or less well for all your inputs, what you can now say? That I am now having a set of weight which gives me sufficiently accurate result for all my inputs. So, if I now provide an input which doesn't match with any one of the previously presented input, let it be an unknown input, which doesn't match with any one of the previously presented input, still with this optimal set of weight, you should be able to achieve sufficiently good result. So the neural network not just memorizes, it doesn't just work for the examples that you have provided, but it can also make quite sufficient guess even if the input is completely new and it doesn't match with any one of your previously presented inputs. And that is the beauty of this model, that it can work, it can interpolate, and even to some extent it can extrapolate the knowledge. And that's why we call it intelligent, because you have trained the neural network with some set of inputs. Now you provide a completely different input, and the neural network can provide a very good guess even out of that unknown input, that what the corresponding output will be. So as engineer, you can understand that what can be the importance of these, because many of the real world problems that you solve in engineering requires modeling, and modeling requires sufficient knowledge of the system. Most of the time we do not have sufficient knowledge. Then we can take this alternative approach, that if we simply have data, suppose if you are running a plant, right? You have an industrial plant or a process, and you want to model the plant or the process, but you don't have the ability to do that because you don't have adequate knowledge. Now simply based on the operational data, right? Because the plant has certain inputs and the plant has certain output. If you have collected historical data of the plant operation, that well, these are my inputs and these are the corresponding plant output. If these data are available, then with this data you can have an alternative approach. You can use a neural network to model the plant, and once you model the plant, now even if you provide an unknown input, you can guess what the plant output should be. So that is quite an important and very useful, it can serve as a very useful, I would say, model for our many engineering applications. So the supervised and unsupervised learning, I just talked about supervised way of learning. There is also something called unsupervised learning. I will show some example of that as well. Unsupervised learning it works in a slightly different manner. There is nothing called input-output combination in this case. So you cannot say what the output should be for this particular input. So you actually don't. They again are very useful, particularly for applications like pattern recognition, right? The example I had given, that character recognition, etc. In this kind of application, this unsupervised learning algorithm works very well. So I'll give example of both. So let me skip some of these topics, right, because I don't think I can cover everything. So let us come to the application domain. So look at the broad domain of application of neurointelligence or artificial intelligence. So you can see that the domain of application can be very diverse, right? So starting from the financial sector, then medical science, sales and marketing, power and energy, computer science and engineering, and there can be virtually every sphere of life, right? Anywhere this machine learning and pattern recognition can find application. Coming to the financial applications, these are the broad domains. For example, the stock market prediction. Like say, in fact, in many developed countries, this stock market prediction, financial forecasting, these are nowadays completely being handled by these machine learning algorithms. And basically the stock market prediction means that we know that in our stock market there are thousands of stocks listed, right? And every day there is a price movement, right? Some of the stocks move higher, some of the stocks decline in value. So whether it is possible to predict that what will be the way of or the direction of the market, say on the next day, next week, or say 6 months from now, 1 year from now. So basically kind of forecasting and prediction kind of application. But there are so many parameters, they actually influence the direction of the stock market that it is very difficult for even the expert market analyst to give very correct prediction of the market, right? In fact, short-term prediction is always, it is said to be very difficult for the markets. So nowadays, we very widely depend on these machine learning and pattern recognition algorithms, right? In fact, as you know that something called mutual funds, right? The fund managers, there are fund managers which basically collect money from investors and then they invest in stocks. They run the fund. So these fund managers, they depend on these machine learning tools, right? And they say that these machine learning tools, they work much better than the human analyst, right? Because there are always human biases, right? These machine learning algorithms, they don't have that human biases. So they actually work much superior compared to the human intervention. Then comes the credit rating determination. So the credit rating determination means that suppose you are a lender, right? You are a lending institute, you are a bank or a financial institute. You lend money to other people. So a customer comes and asks for loan. So that customer's credit rating is being analyzed, right? That how credit worthy that person is, whether giving loan to that person is safe or not. So looking to the credit history of the person, other parameters, his annual income, his family, how many members he has, his dependents, etc., etc. So many different factors, and ultimately based on that, the machine learning algorithm can take a decision whether the loan should be given to the person or not. So this has made the day-to-day task for these financial institutes much easier. Then property appraisal, fraud detection, price forecasting, GDP growth forecasting, all these are nowadays being exclusively done by these machine learning algorithms. Human intervention or the traditional statistical methods, mathematical analysis, these have become almost obsolete. Almost everything is nowadays being handled by this machine learning. Then in medical science, coming to medical diagnosis, medical image analysis, hospitalization length forecasting, treatment cost estimation. You know that this telemedicine, right, and these things, which also require the IoT and IT infrastructure, but this medical diagnosis, we know that telemedicine, where you have a distant, say, a rural hospital, right, where you don't have the expert doctors. So you have taken, suppose, an ECG of a person, right? Someone has come for a patient has come for a treatment and an ECG has been done. So they have the imaging machine, but the problem is that who will analyze that image, because the expert doctor is not there. So then you can use these machine learning tools and the pattern recognition algorithms if these are sufficiently trained, right, because they have a good database. And these databases are monitored by the expert doctors also. So if there is any kind of incorrectness, that can be corrected. So then this can become very, very handy and useful, because in those remote areas where you actually don't have the expert doctors present, then this machine learning based pattern recognition, etc., that can save the lives. Coming to the sales and marketing, sales forecasting, consumer categorization, retail margin forecasting. So sales forecasting for someone who is in the domain of, say, selling something, that what is going to be the sales demand, right, the next month, the next quarter, 6 months from now. that becomes very important. Because based on that sales demand forecasting, the inventory will be maintained. Then consumer categorization. Suppose you are running a, say, shopping mall or say a departmental store, then you have variety of items, right? So depending on your, say, in which area the mall is or the departmental store is, what kind of consumer you have, they make a consumer categorization, that is which particular income bracket requires which kind of a product, right? That which particular category of consumers consume which particular category of products. Based on that, they can maintain their inventory and stock. So all these are nowadays being handled by these machine learning algorithms. Coming to the power and energy, which we'll discuss more in details, electrical load forecasting. You know the importance of load forecasting, because if you are in planning and development, then how much capacity you require, say 10 years from now, 5 years from now, based on that you have to plan accordingly, right? Because you know that this generation, transmission, infrastructure building, right? They require a long time, long gestation period, right? So if you start building a plant today, then it will come to production maybe say 5 years from now, 7 years from now. So you have to make advanced planning. So depending on the predicted future load, you have to plan in advance. So prediction of gas and coal prices, power system control, power plant monitoring, signal processing, all these are now being handled by AI and machine learning. And computer science and engineering, because it's after all a topic of computer science itself, so they have wide applications. So now I will try to give you some specific examples, right? So because not everyone is from power system background, so what I have done is I have kept some very basic examples, general examples, not specific to power system. Then gradually I will try to focus more on one or two power system examples, right? In which domain these applications can be useful. So let me start. The first application is of supervised learning ANN. So as I said, I will be starting with a very general one, right? This is not specific to power system or electrical engineering. Very general one, which is supervised learning ANN as universal function approximator. So let us look at this example, then it will be self-explanatory. So what we are trying to achieve here is that it is predicting the single phase active power consumed by a load, right? Active power consumed by a single phase load. So just imagine that because we are all electrical engineers, we know that this active power P is a function of three variables, right? One is the magnitude of voltage P, the magnitude of current, and thirdly the phase angle difference between the voltage and current, right? Or the cosine of the phase angle. So because we are electrical engineer, we are familiar with electrical active power, so we know that P is equal to VI cos phi. Now just imagine that somebody who doesn't know that how active power depends on these three variables, voltage, angle and current, how to predict the active power for a given value of voltage, current and angle, right? Somebody who doesn't know that P is equal to VI cos phi, he or she only knows that P is a function of VI and phi, but what that function is not known. Right? So then, whether it is possible to predict the value of power if only the value of VI and phi are known, but the function is unknown, right? That is the concept. So what can be done? So as I said that all these ANN based approaches are basically data driven approaches. So you have to provide data or examples to the neural network. So in what form? So look at this table. You have to provide examples of voltage, current, angle and corresponding value of power. So as you can see from the table that individually voltage, current and phase angle has been varied over a very wide range. For example, voltage has been varied from 10 volt to 100 volt, current has been varied from 1 ampere to 2.8 ampere, phase angle has been varied from 0 to 90 degrees, right? So these are, you can say, range of the variables. So the voltage range is from 10 to 100 volt or like that. Current range is 1 ampere to 2.8 ampere in step of 0.1 ampere and the phase angle range is 0 to 90 degrees. Now corresponding to each and every combination of voltage, current and phase angle, the corresponding value of power has been computed. How it has been computed? Because we know the function that P is equal to Vi cos phi. So putting the value of the variables in that function, the corresponding value of power has been computed. So this table is our data table or example table. Now we will feed this example to a neural network. How? This is our neural network architecture. Look at the architecture. So we have chosen 3 number of neurons in the input layer because we have 3 input variables: voltage, current and phase angle, right? We also have just 1 neuron in the output layer because only predicted output, we have to make prediction for the active power P. So we have P as the output variable. In between, I have just 1 hidden layer and the number of hidden layer neuron is unknown, right? It is undefined. You can choose any number. You can start with a small number, say 5 or 6 or 10. But then, if you do not get the desired accuracy, you can increase the number of neurons in the hidden layer, or you can, if required, even add more number of hidden layers, right? So this is how we will proceed. Now, as I said, we will feed this example data to the neural network. How? That when the value of voltage is say 10 volt, the magnitude of current is say 1 ampere, and the phase angle is 0 degrees, the corresponding value of power should be 10 watt. If we change the voltage to 15 volt, current to 1.1 ampere or the angle to 5 degrees, the corresponding power will be 5 watt. So all these individual examples will be fed to the neural network. And as I said, the learning algorithm will try to optimize the connection weights, right? So it will be an iterative procedure. Maybe it will require say 50 iterations or 70 iterations or 100 iterations to optimize the weights. When the weights are optimized, what can you expect? Look at this table, that once the weights are perfectly optimized, how would you know that the weights are optimized? This will be based on the evaluation of the error, right? So as I said, that the neural network will provide a prediction of the power and the actual target power you already know. So we will make a comparison between the two. There's a predicted output and the actual target output. And the difference will be called the error. So until and unless the error drops below a certain threshold value, which can again be set by you, right? The threshold value can be a very small number, maybe say 0.01, 0.001 like that. So once the error falls below that threshold value, then you would say that, well, the weights have been properly optimized and now I can stop training, right? So once the training is completed, now you can look at this data that you can now add some unknown inputs. What I mean is that if you consider these blue colored rows, you see that these values of voltage, current and angle, these were not included in the training data, isn't it? Because the training data are basically the rest of the data. Whereas these blue colored rows, they contain the value of voltage, current, angle, which were previously not shown to the neural network. They were not used for training. So, we will now evaluate the performance the prediction accuracy of the neural network with this unknown sample of input data, right? So look at this table. When the value of voltage is 28 volt, current is 1.3 ampere and the phase angle is 17 degrees, then the predicted value of power by the neural network is 35 watt. That's how the neural network is predicting the power. Whereas the actual value of power, if you put these values in the equation P is equal to VI cos phi, then the actual power also comes out to be 35 watt. So you see that the prediction is very good. Look at the other cases. The value of voltage is 54 volt, current is 1.9 ampere, the phase angle is 43 degrees. Actual power is 75 watt as per the function, whereas the predicted power is 74 watt. Again, the accuracy is very close, right? So this example is to show that with even a minimal set of input-output combination, if you train your neural network, you can still make sufficiently good prediction, right? And this is not just true for a function like P is equal to VI cos phi, but this can be extended to even much more complicated functions, right? Very complex polynomials, trigonometric functions, logarithmic functions, any sort of mathematical function you can model like this, right? So even the classical techniques like curve fitting, etc., right? Even those techniques sometimes struggle to give you so much accuracy, right? So neural network is such a powerful tool that you can see with such a minimal effort, with such a small set of example data, you have been able to train the neural network to predict any complex mathematical function, right? And once the neural network is trained, whatever value of voltage, current, angle you input to the neural network, the network will be able to provide a very correct prediction of the output. So, simple example, but can be extended to any branch of engineering, any practical problems. And you just don't need to go into the mathematical details. Simply, you need the data, right? Now you can ask that how to get the data. Where can I find the data? Data you can collect from the field. Suppose you are going to model some process. It may be a field process, right? Let us take a very general example. Suppose, can be like this, suppose it's an agricultural application, right? Suppose you want to predict crop yield, right? The term crop yield basically means that, say, per hectare of land, how much quintal of rice will be produced, right? So that is basically called the crop yield, right? The quintal of rice, quintal of wheat per hectare of land. Now this crop yield can be a function of multiple variables, as we can all understand, right? We are not agricultural engineers, but still we can understand that the crop yield will be a function of multiple variables. For example, there should be an environmental factor or a weather factor, right? It could be a function of temperature, humidity, groundwater condition, seasonality, etc., etc. So many variables will be present. Now, suppose an agricultural engineer, if he or she tries to, say, model this crop yield problem, then probably a mathematical model will be developed, right? That how these individual variables or the input parameters ultimately decides your crop yield for that particular year. B, we can take an alternative approach. We can take historical data. Suppose if you have the historical data for last 5 years, last 10 years, last 15 years, that these were the environmental conditions, this was the temperature, this was the humidity, this was the groundwater, this was the rainfall, etc., etc., and the corresponding crop yield was like that. Just take this input data, historical data, train your neural network with this data, and then you will find that with this data, you can make a very good prediction. So even for the future years, this input and output data with which you have trained your neural network Once the training is done properly, it will be able to give you a correct prediction that what the future crop yield will be. So as I said, simple example, but application can be in any branch of engineering and science and virtually everything. Now, that same example or the same concept, how this can be used in an electrical application, right? So let me show a simple example, electrical power system problem, that how this concept of function approximation, why we are saying function approximation, because we are actually not developing the mathematical function, or we are actually not predicting the function, right? We are not predicting that P is equal to Vi cos phi. We are actually trying to approximate the function. So what that approximate function is, that we do not know, because neural network is not going to tell you what function it has internally developed, right? So that function is unknown to us. We don't need to know that, because we as user will be using the neural network just as a black box. So our objective is only to provide the data and to get the output. What goes internally, we are not interested about, right? Of course, the training algorithm should be known to us. We should understand the background, we should understand the process by which these training algorithms work. But for a specific problem, you don't need to know what exact mathematical function the neural network has predicted. You are only interested about the results, right? So let me show this concept in a power system problem. So what that problem is, it is voltage stability enhancement using ANN assisted power network reconfiguration. So let me just give you a very broad idea that what this problem is. I think for many of you, this term like voltage stability, network reconfiguration, you should be familiar. For those who are not from power system background, let me just try to give you some very basic idea that voltage stability is an issue for the modern power system, right? We know that as per the regulatory provisions, that voltage at the consumer's terminal, it has to be maintained within a specified limit. And to be specific, that limit is from 0.95 per unit on the lower side to the 1.05 per unit on the higher side, right? 1 per unit being the nominal value. That means from 95% to 105% of the nominal value. That much of tolerance is permitted, not beyond that. Now the problem is that the modern power systems, they are very much stressed in the sense that because of the economic reason, because every power generator, power system operator, distributor, they try to maximize their profits. So generally they run their network, the generation capacity, transmission capacity, distribution capacity to close to the maximum limit, right? As much as possible to harness from the network. The problem is that when you push the network to its limit and the network is overstressed, then you find some sort of parameter variations or degradation of performance quality. One such degradation happens in terms of voltage. As I said that the node voltages or the voltage at consumer terminals has to be maintained within the specified band. But when a network is overloaded, for example, suppose if your active and reactive power loads exceed the normal value, then there is a possibility that there will be a drop in voltage at the consumer terminal. Once the voltage drops below 0.95 per unit, it is unacceptable, right? And also, if the network is very heavily stressed, sometimes what happens is that the voltage steadily declines and it can also become unstable and the voltage can suddenly collapse. So this is called the voltage stability problem, and many modern power networks have faced these issues in the past. So the regulatory framework has also been enhanced that such problems do not occur in the future. So the power system operators, they Every time they try that the network is maintained properly, right? The network parameters are maintained. So stability, both rotor angle stability, frequency stability, as well as the voltage stability, these are being ensured, right, in day-to-day operation of the power system. Now, voltage stability enhancement, it usually requires some hardware-based investment, right? Because you know that if you wish to maintain a proper voltage level, even under very heavily stressed condition, you need to have additional reactive power support. So where from you get that additional reactive power support? By installing bar compensating devices. So you either install static capacitor bank, you can also have static bar compensators, or you can also have synchronous condensers. So these are the things, generally they provide the additional reactive power when the network is highly stressed. So by injecting additional reactive power, you can maintain system voltage. But all these require additional investment, right? So no power system operator would be interested in investing more only for the sake of maintaining voltage, right? Now this network reconfiguration can be an alternative approach. What is that alternative approach? The network reconfiguration basically means that generally you will find that in any power network there are a lot of redundancy available. Means between any pair of buses, you will find sometimes there are parallel path available for the power to flow. For example, there can be parallel set of transmission lines, right? Or there could be multiple connectivity between the buses. Now, these multiple connectivities are generally done to ensure reliability, right? That in case one of the line trips or one of the path breaks, the power can still flow through the other path. Sometimes some of the loads are so critical that you require this redundancy. Now, whether this redundancy improves system performance, that we cannot say for sure. It definitely improves reliability, but in terms of performance like network power losses, efficiency, voltage levels, voltage stability, additional power lines may not always be the optimal idea, right? So you always have the scope for reconfiguring your network, right? Suppose originally the network was configured in a certain way, but that configuration may not be optimal because when it was designed, maybe that the optimality check was not done. Not just that. Suppose a network has been designed today based on the present load. Now in future, there will be load expansion, there will be augmentation of generation also. So depending on the new load generation scenario, the same configuration may not provide you the best result. So you need to require to change the power network reconfiguration can also lead to improvement of the voltage and enhancement of the voltage stability, right? So that is exactly our objective, that let us check that which particular network configuration gives me the optimal performance for a given load generation condition, right? Now this is easier said than done because when you have a large network, there could be multiple number of connectivities, right? So which particular connectivity, which particular line between the nodes will give you the best result, that requires extensive analysis because it's not a matter of simple task because you know that you have to perform load flow analysis to evaluate that how each and every individual configuration works, right? So it's a tedious task. Now we are proposing a neural network based network reconfiguration. Why we are proposing neural network? Because as I said, for a large network, if you consider any two pair of buses, suppose you have a 30 bus network, right? So between any two pair of buses, you can have multiple lines possible. So this way, if you just take the permutation and combinations, then the total number of connectivities can be hundreds and thousands. So out of these thousands of connectivity which are theoretically possible, which one will be optimal for a given load and generation scenario, that needs to be checked. And if you are going to do it manually by running your load flow programs repeatedly and repeatedly, it will take days. So it is practically impossible, because if you are a power system operator and if you are now sitting on a substation or a power station, you have to take an instant decision that, well, my load situation has changed, my generation situation has changed. What should be my optimal configuration which will give me the best solution under the given situation? So you cannot afford to have such a long analysis time to get the results and then to configure your network. So you have to make an instant analysis and instant decision. So let us see how neural network can do this. So as I said, the neural networks are basically data-driven approach, right? So what you will do is that, let me skip some of these slides because I have already given you some basics of this idea. So let me straight away go to the diagram. For example, this is basically a case study. This case study is on a relatively smaller system. It's an IEEE 14 bus system. And you can say it's a modified IEEE 14 bus system because some of the interconnection between the buses have been changed, right? So as you can say, it's a 14 bus network, and you can see that there exist power lines connecting the buses, and for many pair of buses there exists more than one transmission line. So there are parallel lines as well. Now you can see that in some of the lines we have deliberately put some switches, right? For example, one switch is here, one switch is here, one switch is here, like this. What is the purpose of this switch? These switches, they will enable you to open or close a particular line. So not every line can be opened and closed, right? Some of the lines may be permanently there because some may be very vital lines, power carrying lines, so you cannot open those lines. Some of the redundant lines can be opened or closed. So you first decide that which are the lines which we will open or close. And accordingly, you can have circuit breakers or switches placed on those particular lines, right? So you can have a switch over here, as here, or here. So when you close the switch, that particular line is connected between the buses. When you open the line, open the switch, that particular line is disconnected from the system. Now, what you do here is that, look at this table, what the idea is. You can see there are three switches, right? S1, S2 and S3, right? And these zeros and ones actually indicate the switch status. 0 means a particular switch is open. 1 means that particular switch is closed. So this opening and closing will decide that which line will be connected and which line will be disconnected. Now what we are trying to do, we have named the system configurations accordingly. I have just shown 7 system configurations, but in reality, the number of configuration can be hundreds or even thousands, right? Because there can be multiple combinations, right? You open one, you close another, you open something else. So this way, the number of combinations can be huge for a large system. So I have just shown 7 combinations for the 3 switches. Now, what is your objective here? The objective here is to check that which combination gives me what kind of a result. So what we are going to study is that we have chosen one particular index. Now those of you who are from power system backgrounds, they should already be knowing that we have certain indicators of voltage stability, right? Normally we measure the voltage stability in terms of voltage stability index. So index is something, index is basically has a range, right? For example, the index which has been used here is called the L index. L index has a range between 0 to 1. And this value of L index gives you an indication that how good the system's voltage stability condition is, right? So as I said that the voltage stability depends on so many different factors. So when you have good stability condition, the value of the index will be close to 0. And when the voltage stability declines, the index will shift towards 1, right? So looking at the value of index, you can have a broad idea that how well the voltage stability condition of the system is. Now, this index value or the voltage stability condition of the system will vary according to load generation scenario, right? So for a given load generation scenario, the voltage stability condition may be something and the value of L index may be something. When you change the load generation scenario, the index may completely change, right? It may improve, it may deteriorate also. Now look at this table. I have used several columns. What are these columns? These columns give you the corresponding condition of the load. So the first column is for normal loading condition of the system. And the rest of the columns are basically the changed values of the loads, normally increased load, right? So when you are increasing the load, how the index is changing, right? Or when you decrease the load, how the index is changing. Now you can see that for a given, now if you concentrate on a particular loading condition, right? Suppose the loading is now fixed. Let us assume that the loading is at normal value. Now if you change the switch status, you can see that within the normal loading condition, you get different values of index, right? So for each and every different combination of switches, the value of index is different. What does it mean? It means that the value of index is sensitive to the network connectivity. So when the network connectivity changes, even if the load is not changed, the value of L index, that means the stability of the system, will undergo a change, right? Now you see that the smallest value of L index gives you the best stability, because as I said, values closer to 0 means the system is more stable, values close to 1 means system is approaching towards instability. So you see that for normal loading, when all the 3 lines are removed from the system and the switch status is 0, 0, 0, that means all the 3 lines have been removed from the system, you have the worst condition, right? Where the value of L index is 0.2758. When one switch number S3 is closed, you find that the value of the index, so let me use the pointer here. So the value of this index comes out to be 0.2426. When S2 is closed, other 2 switches are open, you get a value of 0.274. When all the 3 switches are closed, the value drops to 0.1899. So that means for normal loading, when you have all the 3 lines present, you get the best voltage stability condition when all the 3 lines are present in the system. But that may not be the case for other loading. So what are the loading scenario? You see that load 1 means 70% increase of load at bus number 10 and 30% decrease of load at bus number 5 and 14. So this is arbitrary. You can take any loading condition. I have just taken few examples. Similarly, load 2 means 70% increase of load at bus number 10, 30% decrease of load at bus number 5, 14, and this should be 17 probably. Anyway, so these are the loading conditions and the corresponding value of index when the load is at 2, right? So again, you see that this particular switching combination 101 means S1 is closed, S2 is open and S3 is closed. That gives you the optimal value of L index, that means the best stability condition. Similarly, when you have loading scenario number 3, then again this 101 combination gives you the best solution. So what is the observation? The observation here is that having all the three lines closed or present may not give you the best solution under all loading conditions. So different loading conditions gives you different combinations or different line status which will give you the best result. Now the question is, because load generation scenario can vary over a wide range. So when you are a system operator operating the system, every hour you find there is a change in load and change in generation. So is it possible for you to predict that what particular switching status will be optimal for that combination? Very difficult to predict manually. So then we go for a neural network based prediction, right? So what we exactly do here is that we train a neural network with these examples that, well, if this is my loading condition, then this set of switching combination gives me the best solution. If the loading situation changes, then another switching combination gives me the optimal solution. So this way, you create examples. How do you create examples? There are two possibilities. One is, if you have access to a real-time system, suppose if you are a grid operator, if you are sitting on, say, ERLDC or SRLDC, then sitting at the SLDC you can say that, well, these are my daily variation of load, and if I am able to change the configuration manually, then this is the result that I am getting. But generally this is theoretically possible, right? Because even sitting at SLDC or ERLDC, it is not possible to monitor the load 24/7 and then change the switching combination and then check the status again. That is not possible. So alternatively, what we normally do is that we develop a computer model or a mathematical model of the system using any platform. It could be MATLAB, it could be ETAP, it could be PSCAD, anything. So we develop a mathematical model of the system, then we actually simulate these changes, right? That means we close a line, open a line, change the loading condition, change generation. All these variation in the system's operating condition, we create them and then check the results by running load flow program multiple number of times. So this way we create our training data set. So this acts as the example for the neural network that, well, when this is the loading scenario, this set of switching combination gives me the best solution. For a changed loading condition, another set of switching combination gives me the best solution. With this data, you train the neural network. Once the neural network is trained, now the application part is very simple. Because now the neural network has been completely trained, simply provide the data for loading. That, well, this is my current loading scenario. And you ask the neural network to predict that which particular switching combination will provide me the best solution. And the neural network will provide you the correct prediction. I just show you the result table. You see that on the left hand side, you have the variation of active and reactive power load, right? So on this side, you have this variation of active power, here you have the variation of reactive power. Now, these are the best switching combinations which are actual. Actual means we have actually done the analysis, running load flow program, and we have found these switching combinations to be the best or the optimal for this particular loading situation, right? So we can say that these are actual switching combination which should provide the best solution. Let us now see what neural network is predicting. You see that when the actual switching combination is 0, 0, 0, then the neural network prediction is 0.015, 0.031 and 0.012. Take another example. Suppose, let us take this example. When P is 61%, Q is 41%. Actual switching combination which should provide you the best solution is 0, 1, 1. That means S1 open, S2 closed, S3 closed. What neural network is predicting? Neural network is again predicting 0.026, 0.954 and 0.947. So if you just truncate these values to the closest integer, these are 0, 1, 1. So you see that almost in all cases, the neural network is giving you a very correct prediction. So this is a practical example of how mathematical modeling of functions can be utilized in power system problem or any engineering problem. Because this is again a complex function approximation problem. Because see, this voltage stability index is a function of several factors. One is the configuration of the network, the connectivity of the lines, and the loading, right? So this load connectivity results in a particular value of L index. So L index is a complex function of network connectivity and loading scenario. But what that function is, we do not know, because it's a very complex function. But if we take this alternative approach, we actually don't require mathematical modeling, because the neural network, based on the training data, will now be able to give you a correct prediction for a given load generation scenario, which particular switching combination will be optimal, right? So small example, but can be very useful. Okay, now I again would like to give you, I think I have very limited time anyway. Okay, let me give you this example that how unsupervised learning neural network can be used. It's again a very general example. This is for alphabet recognition. I have given an example of handwritten digit recognition. This is for alphabet recognition. So what the purpose is that we have 26 alphabets in English, right? A to Z. So we have to recognize each and every alphabet. And it may not be the typed alphabets. It can be handwritten alphabets as well. So we even have to recognize correctly the handwritten alphabetic characters. So how we can do this? That we have 26 alphabets, right? So we have to train the neural network to recognize each and every individual alphabet. How can we do that? So for that, every alphabetic character has to be converted into the corresponding data stream. How can that be done? Look at this example. So here what we have done is that we have mapped individual alphabets onto some two-dimensional space, right? You can call it a 2D space on which the alphabets have been mapped. And we have divided the space. The space has a defined size and shape. And we have divided that space into a given number of cells. So we have chosen to divide this space into 16 number of columns and 20 number of rows, right? So this way, 16 into 20, that means 320 cells have been created. That means you can say that this alphabet has been mapped onto a space which comprises of 320 number of cells, right? Same thing applies for the next alphabet also. The alphabet K also has been mapped onto a space and has been, this is basically called discretization or pixelization of the alphabet, right? We are trying to find out individual pixels. So you can call each and every cell as a pixel. So now you can see that when an alphabet has been mapped, most of the pixels are basically empty pixels or they are white pixels, and the occupied pixels are basically these dark pixels or the black pixels, right? I'm just talking about the black and white. Now what you can do is that the empty pixels can be assigned a value of 0 and the dark pixels can be assigned value of 1. And based on that, what we are doing is that we are converting each and every alphabet into a corresponding data stream. How? For example, look at the alphabet A. Alphabet A has been converted into a matrix. and this matrix comprises of most of the elements being 0 and only few of the elements having a value of 1. So occupied pixels have a value of 1, empty pixels have a value of 0, right? So in the first row, only the 8th and 9th pixels have value of 1, rest of the pixels or the rest of the elements have 0 value. Now, if we just write the rows side by side, first row followed by the second row followed by the third row, this way, the last row is the 20th row, then you get a vector of dimension 320 elements, right? And out of these 320 elements, some specific elements will have value of 1, other elements will have a value of 0. You can say that this particular vector is a representative of the alphabet A, right? Same thing can be repeated for the alphabet B or the alphabet C or the alphabet S or the alphabet T or the alphabet Z. So what does it mean? It means that now you have 26 vectors for alphabets A to Z, and each of these vectors are unique in nature because no two vectors are identical, because the vector corresponding to A will be different from the vector corresponding to B, and it will be different from the vector corresponding to C, right? So this way now you create a database of 26 vectors, each representing one particular alphabet. What is your job now? The job is now to feed this data into a neural network or any pattern recognition algorithm, and the pattern recognition algorithm should be able to correctly identify, distinguish between all these 26 vectors. We call it output classes. So each and every alphabet will be put into one particular class. So alphabet for class A, we may call it, say, class 1. Alphabet classes, right? Now, this is not enough because we are so far working only on the typed, proper shaped alphabets. But actual handwritten alphabets can look very different. So look at this example. See, what we have done, in addition to the original alphabet A, we have added 3 more variants of A. And these variants look very, very different. They don't look like the original alphabet. So sometimes the data is slightly corrupted. Data may be slightly noisy. So as a result of that, you see that the rest of the alphabets significantly differ from the original alphabet. Same goes true for the alphabet B also. One is the original one, but the others are very different. So this way, we are adding 4 examples of every individual alphabet. So 4 different examples of A, 4 different examples of B, 4 different examples of C, and so on. What is the idea? The idea is to make the neural network learn that, well, A can have so many different variations possible. B can also have so many different variations possible, right? Once you do this, your objective is now to look that, well, all A's should be put into one single class, right? If the original A has been put into class 1, then this deformed, corrupted or noisy A should also fall into class 1, right? It must not go to some other class. So that's what we need to check. Now, if we just go back to this previous table, you can see that there is something called a class index. This index has been returned by the pattern recognition algorithm. What this index suggests? See, these index values are generated by the network, and the index will differ when you run the program multiple number of times. So you run it for the first time, you get one set of index. You run it for the second time, you get a different value of index. That doesn't matter. What matters is that there should not be repetition of the same index, because the index tells you what is the alphabetic class it is. For example, in this particular iteration, alphabet A has been put into class 26. Alphabet B has been put into class 27. C has been put into 14. D has been put into 13. Like this. But if you check, you will find numbers ranging from 1 to 26. But no number repeats twice. What does it mean? It means that all the 26 alphabets have been recognized correctly and they have been put into different classes. If two alphabets would be assigned same index, what would it mean? It would mean that the pattern recognition algorithm has not been able to distinguish between those two alphabets, and the algorithm has put those two alphabets into the same class. That should not happen. So we see that all the alphabets have been assigned distinct value of index. No index has been repeated twice. Fine. Now let us broaden this thing. That means let us now also add the deformed, noisy, corrupted alphabets. And let us see whether all those corrupted alphabets also belong to the class of the same, the original alphabet or not. Right? That is our objective. Now look at this result table. This is basically a schematic or pictorial representation, but what you see in this diagram is that you have basically 26 boxes created here. What each particular box indicates, you see that boxes have been numbered, and these numbers are corresponding to the index. For example, this box, this red colored box has an index of 1. This blue colored box has an index of 2. Yellow has an index of 3, and so on. Right? Now, if you go back to our original table, you see that alphabet A has an index of 26. Look at this particular table. You see that this last box, which has an index of 26, all the A's should actually belong to this particular box. Look at the first box. This is for index number 1. Go back to the table. See, index 1 is for alphabet X. So all X should fall into that particular box which has an index of 1. Now, if you look at this table, you see that most cases, look at the first box. You see this X1, X2, X3 and X4. What are these X2, X1, X2, X3, X4? These are the 4 variants of the alphabet X. They all belong to the same box. That means the pattern recognition algorithm has been able to identify all the variants of X as X, and they have been put into the same box. But there are some cases of misclassification. For example, look at these red colored ones. These red colored ones are basically misclassification. For example, look at this. A2 has been put into this box. That means the network thinks, or the pattern recognition algorithm thinks, that the second variant of A looks similar to X, and that's why it has put into the box of X. So it's a case of misclassification. Similarly, look at this example. E3 has been put into the box of C. That means the pattern recognition algorithm has seen the third example of E similar to that of C, and that's why it has put into the box which has been assigned the index of 14. So these are few cases of misclassification. But if you count the overall number of misclassification, you see that out of this, how many examples are there? 26 alphabets, each having 4 variants. So altogether there are 104 such examples. Out of 104, you find the number of misclassification is 1, 2, 3, 4, 5, 6, 7 and 8. That means 8 out of 104 are misclassified. Rest are correct classifications. So even with such minimal set of data, and you see that the variation is quite significant, isn't it? In some cases, the alphabets are so much distorted, so much corrupted, that even for us, it is difficult to recognize them as the alphabet. Still, the network has shown nearly, say, 97-96% accuracy, because out of 104, only there are 8 cases of misclassification. So this kind of pattern recognition algorithm can be very useful. So I think I don't have time to show another power system example because it is already 12. Should I continue or just stop here? I think if you have to maintain the schedule, I have to stop here. Right. Okay, so sorry I couldn't complete the whole thing because I had some more power system examples based on this pattern recognition thing as well. So if you have any queries, doubts, questions, I would be very happy to address them. So please, if you have any question.
One question I have.
Yes.
In the first example, your input was 3, Vi and cos phi.
Right.
And hidden layer was, you can assume, arbitrary. But
Yes.
hidden layer must be 3,
No.
more than 3 or less than 3.
It can be anything actually.
It can be 1.
It can be 1, means, as I said, when you are developing the architecture of the neural network, deciding the architecture, there are 2 mandatory layers. One is the input layer, another is the output layer. Hidden layers are optional. You may or may not have hidden layers. Again, the number of neurons per layer, this is only pre-decided for the input layer and the output layer. See, in the input layer, there are 3 neurons. Why? Because you have 3 components of input or 3 elements in the input. One is the magnitude of voltage, magnitude of current, and the phase angle between the voltage and current. So Vi and phi. So because you have 3 input variables, you have 3 neurons in the input layer. Similarly, you have just one variable to predict, which is the power. So in the output layer, you only have 1 neuron. So number of neurons in the input layer should be 3. Number of neurons in the output layer should be 1. In between, the number of hidden layers can be anything. It can be 1, it can be 2, it can be 3, anything. And also the number of neurons in the hidden layer is also your choice. Normally we try to start with minimum number of hidden layer, that is just 1 hidden layer, and with small number of neurons, maybe 5, 7, 10 number of neurons. Then if we do not get the desired accuracy, either we increase the number of neurons in that hidden layer, or if required, all of them participate in calculating the weighted sum. Because as you see that the information is actually being transmitted layer wise. From the first layer, it goes to the hidden layer. From input layer, goes to the first hidden layer. From first hidden layer, it goes to the second hidden layer. From there to the third hidden layer, and so on. And finally, you get the output.
So another third question is, in every hidden layer, every time I have to specify the minimum error,
No.
0 to 1.
Generally not. There are certain algorithms where there are provision for input, not just from the input layer, but also in between you can provide inputs. But for a simple architecture like this, which is basically, this particular architecture is called multi-layer perceptron network, MLP in short. So for MLP network, the error will only be calculated at the output. Right? And then, generally the MLP networks are trained by an algorithm which is called error backpropagation algorithm or BP algorithm. So this error backpropagation algorithm works in a manner that basically the error is calculated at the output layer, and then this error is propagated backward. That means normally the information propagates forward direction, but the error actually propagates in the backward direction from the output layer to the third hidden layer, to the second hidden layer, to the first hidden layer, this way. So this is a backward propagation, and when this error is back propagated, every stage there is a modification of the connection wave following that particular training algorithm. So the weight optimization happens like that it utilizes the value of error, but the error is propagated in the backward direction. Right? So that is more or less the way it works. Any questions?
Sir, in mathematical modeling, we can see it's a sum of It's a sum of weight multiplied by x.
Weighted inputs.
Yeah, weighted inputs, W1, X1.
Right.
So like, how to decide the weights, means how to define the weights. Weights, the summation of the weights will be 1.
No, not necessarily. The weights are basically random values. Initially, when you first time you run it, right, or when you initialize your program, you basically assign random values of weights. Weights are completely randomized. And these random values can again lie within a specific range. And that range is generally decided by the range of the data. Generally, we prefer normalization. Normalization means all inputs as well as the weights have to be brought to the same range. That means you have seen in the example, the range of voltage, current and phase angle is very different. For example, voltage has a range of 10 to 100 volt. Current, on the other hand, has a range of just 1 to 2.8 ampere. So, normalization helps to bring all the individual elements of input to the same range. Normalization means maybe all these individual inputs like voltage, current, angle will be brought to the same range of say 0 to 1 or -1 to +1, including 0. So that means voltage will be brought to a range of 0 to 1, current will also be brought to 0 to 1, angle will also be brought to 0 to 1. And in that case, the weight values should also lie between 0 to 1.
So how to define that, sir, weights?
It's not defined. These are random values of weight. Only the range is defined.
Okay, that environment, the software environment will decide.
Right. You have to use some sort of a random number generation function to assign random values to the weights initially. But then during the procedure of training, the weights will be iteratively trained. That means the values of weight will be modified, they will be optimized. And once they are optimized, now you will preserve the weights. That means you will store them so that you can reuse those values of weights in future. So that next time you run the program, you don't need to randomize the weight. You can use the already optimized values of weights. Right? This is how it works. Any further question? Okay, so if there is no further question, thank you so much for your patient hearing. Hearing at a stage for 2.5 hours, I understand how difficult it is.
Sir, one question.
Yes.
Then what the main difference between the normal optimization? We are using the normal optimization anything, and in this case, sir, you have told that the optimal solution have been decided by the hidden layer.
Right.
Means
Not the hidden layer, but the values of the weights actually.
wait. In
So-
case of the normal optimization, what we are using, either computer has been decided the random value, or we select.
Right. See, optimization, we can use different algorithms, right? There are some classical methods of optimization. For example, linear programming is one. There are statistical methods. You can also go for different heuristic optimization technique. For example, nowadays we use different heuristic optimization like genetic algorithms, particle swarm optimization. So these are optimization techniques which are used when your application is an optimization kind of problem, right? But here the weight optimization, we do not specifically use any optimization algorithm as such. This training algorithm, the ANN training algorithm itself is a kind of optimization algorithm. For example, this backpropagation learning algorithm, it's not an optimization algorithm, but the way it works is very similar to some sort of an optimization algorithm, right? So we don't need to use any separate optimization technique. The training algorithm itself will take care of optimization.
But sir, to create the hidden layer,
Yes.
we have to put some programming, and that basis on some
No,
optimization or anything else.
Hidden layer you will decide at the beginning that, well, I will choose 2 hidden layers with so many neurons. Then during the training will be performed, then the network will be tested, its output will be checked, that how good the prediction result is. If you are not satisfied, then only you will change the architecture of the network. Then you will say, add more number of hidden layers, or you will delete some of the hidden layers. We will modify the network architecture and we will retrain the network. Training will be performed. Right? So it's not that during training, number of hidden layers will be changed. Once the training is done and the performance evaluated, then only you modify the network architecture. Like that. Any further question? Okay, thank you so much for your questions.
This doesn't ensure that the result will be better if number of hidden layers will be increased.
Not necessarily.
Not necessarily.
Because in neural network there are several issues like overfitting, right? So increasing the number of hidden layers may not always give you a better result. So you have to optimize this set. So optimize means start with a minimal number of hidden layers, just one hidden layer, and then incrementally add more number of hidden layers unless you get the best result, until you get the result.
Thank you, sir, for this wonderful presentation. Now I request our coordinator, Dr. Professor Sumit Banerjee, sir, to give a small token of appreciation from our department.